Hi everybody, welcome to another video in Calculus 1, section 3.9, related rates. So, previous section we learned about implicit differentiation. So we assume y is a function of x, and we take derivative with respect to x, and then we solve for dy over dx or y prime. Right. In this case, we assume that all the variables are the function of another variable, t. For example, we have x squared plus y squared equal to 1. Now suppose both of them are function of t, and now we differentiate with respect to t, both sides. Now since both of them are function of t, I put the parentheses around it, and we take derivative, right? So, derivative of parentheses square is going to be 2 times the parentheses, and then the parentheses. Right, so that's for the first one. And for y squared, we do the same thing. 2 times the parentheses prime. Derivative of 1 is 0, because that's constant. Right. Now we have x in the first pair parentheses, y in the second pair. Right. Now, of course, that gives us 2x, and that was x prime. There's nothing wrong with that. However, since in this case we have more than 2 variables, it is better to write in form of the dx, dy, or dt. So in particular, derivative of x, since we differentiate with respect to t, we will have dx over dt. Then 2y dy over dt. So this is more precise because there are more than 2 variables. We have to specify which one is the dependent variable, which one is independent variable. In this case, derivative of x with respect to t, derivative of y with respect to t. So that's what we have here. Right. Since we have rates, which is derivative, and they are related in an equation, so therefore we have the problem of related rates. So, having said that, the last problem we can just do the same thing, right? Let's say if we have x squared plus y squared equal to 1. Now assume y is a function of x now, but if, now this is 3.8, implicit differentiation. Let's say we differentiate with respect to x. So you can even put the parentheses around it. It's going to be 2 parentheses prime plus 2 then 0. Of course, we can put x, y in there. So it's going to give us 2x. Now this one we have derivative of x, right? So you can just write the x with respect to x, so dx over dx, and that's why this equal to 1. Yeah, so in 3.8 exactly this is what we write. Differentiate with respect to x, so we have just put the parentheses around all of the variables, right? And then differentiate, and then put x in for this one, and then put y in for the other one. Derivative of x, which is dx, with respect to x over dx over dx cancel out is 1. And that's what we have. So, doesn't matter what variable we have, just put the parentheses on all of them. And then differentiate using the chain rule. And then finally, when we have that, derivative of that variable with respect to whatever the variable is. And we're going to write like that. Right. Another way to write like this, although I usually don't write like this, but you might see this in the book or some older textbook. It said differentiate with respect to x on both sides. Rather than spell it out like that, they just said, how about we differentiate with respect to x on both sides. Right. Now, derivative of a sum is the sum of derivative. So we have derivative of x squared plus derivative of y squared, and right hand side still constant. Yeah, right. The derivative of x squared with respect to x, that's 2x. Then the derivative, sorry, this with respect to x, because both of them with respect to x. Yeah, because the variables are different, we have to write this is 2y and then dy over dx equal to 0. Of course, that's still the same thing, but the reason sometimes I just want to spell it out rather than write all of this. In the math book, usually you might see something like this because they don't have to explain anything. That means take derivative both sides with respect to x and do that. My point is, in this case, if we take derivative with respect to that variable, when you put the parentheses in, just replace derivative of that variable with respect to that variable. So derivative of x with respect to t, so dx over dt. Right, so that's what we have. That's what we have. Now let's try another example. Let x squared plus y cubed equal to 5. And just like the last problem, usually we write assume y is a function of x, differentiate something with respect to x. This is the same way. The first thing we should write, suppose that both of them are a function of t. Then we differentiate with respect to t. Right, now with respect to t, so we put everything is function of t, so I put the parentheses around all of the x on the y. Let's write that. So differentiate or take derivative. Let me write this one again. Equal to 5 with respect to x. Sorry, with respect to t, because in this case the question asks us dx over dt, so we know t is the independent variable. So now those are function of t. Now the chain rule saying 2 times the parentheses prime parentheses cube will be 3 times the parentheses square, the parentheses derivative. Derivative of 5, that's a constant, derivative is 0, right? Now we're just going to put x here and then y there. Now 2x, x prime, so this is derivative of x with respect to t, so for that we're going to write dx over dt, and here we have 3y squared, derivative of y with respect to t, so let's write dy over dt. So we want to be more specified which one is a variable, which one is the independent variable. And in this case we solve for dx over dt, derivative of x with respect to t, move that to the other side and divide by 2x. So we have 2x dx over dt, move that to the other side, so divide by 2x on both sides, and we are done. So divide that over negative 3y squared 2x dy dt, dy over dt. So simple enough, right? So assume everything a function of t. Usually in this case this related rate, so usually t represent time, so that's what the rate is for. So that's what we have, right? Assume everything a function of t, take derivative using the chain rule, and then put in the variable and then write using the proper notation derivative of x with respect to t, derivative of y with respect to t. So that's pretty much the whole section, the idea, the whole section. The rest of the section, we just do a bunch of examples. Right, next. Let x squared times y minus 3x equal to 4y plus 3 if find dy over dt. So we know for sure y is a function of t, and we are given this information. Again, dx over dt, so for sure we know x is a function of t as well. So in this case we can say x is a function of t, y is a function of t, or we just say assume x and y are a function of t. And now we differentiate everything with respect to t. That equation now differentiate that with respect to t. Right. Notice one thing though. Everything a function of t, so we can just put the parentheses around all the variable, just to signal that they are a function of t, which is good. Right. Around the first one though, x is a function of t. Definitely x squared will also be a function of t. So a function of t, y is a function of t. So what we have here is a function of t and times the function of t. So that obviously a product rule where we have to use the product rule there. So u equal to x squared and v equal to y. I can put the parentheses around that because they are a function of t, right? So we check derivative. It's going to be 2 times that parentheses prime. Inside the parentheses is x. So that gives us 2x. And x prime here is a function of t, right? Because we differentiate with respect to t. So in that case we have dx over dt. And v, so v prime is equal to y prime. But we're not going to write y prime. We prefer to write dy over dt. So to be more specific, which one is the variable? Which one is dependent variable? Which one is independent variable? Both x and y depends on t, so that's what we have. Now, differentiate this with respect to t. The first one is u prime v, so u prime is going to be this. U prime dv u prime v plus u times v prime. So that's the first one, derivative using the product rule. Okay, I think that's clear enough. Next, derivative of this. That's easy, right? Just a parentheses, so I just say 3 minus 3 times the parentheses equal to 4 times that. And then derivative of 3 is 0. So we check the derivative of each term. That's what we have. Right, inside the parentheses, just x, then y. Right? So just take the derivative, and that's just that. Because just the parentheses, this doesn't raise to any power. Right, let's just rewrite this a little bit. that gives us 2xy dx over dt plus x squared dy over dt minus 3 x prime, that will be dx over dt because x is a variable that depends on t, equal 4 dy over dt. Right, so that's what we have. Now, what are we trying to solve for? We're trying to solve for dy over dt, right? So this is what we solve for. And so we go after that. We know x is 1, y is -2, and dx over dt is -3. So substitute all the information we want to. Usually this type of problem, we can just move that over and isolate and try to get that by itself. We can do that. But I prefer to just put all the numbers in and get that by itself. That will be easier. So for this, those are the values we know. So at x equal to 1, y is -2, and dx over dt is -3. We substitute those values into the equation here. Notice there's a plus here, subtract, and then, yeah. So I have 2, x is 1, y is -2, dx over dt -3, plus x squared, 1 square, dy over dt. We're trying to solve for that, so we don't substitute for it. Minus 3 times dx over dt, which is -3, equal to 4 dy over dt. We solve for it. So right now, 2 times -2 times -3, so that 2 -4 12. 1 square is 1, so we just have 1 12. I mean 1 dy over dt minus 3 times -3, that's plus 9, equal to 4 dy over dt. Combine like terms, 12 plus 9 is 21, and I move dy minus dy over dt to the other side. So 12 and 9, that's 21. And 4 dy over dt minus 4 dy over dt, 4 of them minus 1, we have 3 dy over dt. And then to solve for dy over dt by itself. So dy over dt is 21 over 3. Which is 7. Right, so it's not that bad. So assume that everything is function of t. So we just take derivative. This happened to be a product rule because we have x times y. I mean the function of t times a function of t. So that is the product rule. Right. So in terms of math, that's all we have. The rest of the problem, we have a bunch of application problem. Because after all, this is related rate, and the rate is the change of something over a change in time. So that's what we have. Right, let's look at this problem. So usually when we see a work problem that related rate, where we see a bunch of rate like this, it's more likely it is related rate, especially divided by unit of time. Right, so just like the cookbook, just read and then just get some idea. Of course, that's not going to help us to solve the problem, but just more like a guideline. Right, to read the problem, sketch and identify the rate, and the rate that is given, and the rate that is to be determined. Right, write one or more equation that express the basic relation between variables. So that's useful. So first of all, we have to identify the rate and then write the equation. So something relation amongst the variables. And then we take the derivative both sides with respect to t. And then we solve for what we have. Usually when we do this and we take the derivative, we have the problem, just like the problem we did. But we have to go from the work problem, from an application problem into an equation first. From there we can take the derivative with respect to t. That part should be easy after that. Right, now, so let's apply that to the problem that we have here. So, two small planes approach an airport. One fly due west, so this one goes west. And the other one due north, so that one goes north. Assuming they fly at the same constant elevation, so it's not like one fly above and then one fly at the bottom. So just everything on the same plane. So we only deal with two-dimensional rather than three. Right. How fast is the distance between the plane changing when the westbound plane is 180 miles from the airport and the northbound plane is 225 miles per airport? So when we look at the problem, first identify all the numbers. That might give us a clue what we're talking about, what we need, what are we dealing with. Right, so first of all we have 120 miles per hour. Identify all the rate, 120, 150 miles per hour. Those are the rates. And the question is, how fast is the distance changing? So that also a rate, but we need to solve for it. And then we have two numbers. And so those are the units. That's what we focus on. Now we try to draw a diagram. The airport here, an airplane that going west, due west, 120 miles per hour, and then north is 150 miles per hour. So when we draw this, we see, is there any relation? So let's say one going west and one going north. They should be perpendicular to each other, especially they are on the same plane. Right, so they're perpendicular to each other. And let's see the plane that going east or west, that horizontal, the other one vertical. So in this case, if we let x be this distance from the airplane, from the westbound plane to the airport, and we're going to let y be this distance from the northbound plane to the airport. And we will let the distance between them, distance between the airplane be z. Hit the roller. So those look like the variable we have x, y, and z. So how they related? Especially the right triangle, right? So the equation we can come up with, of course, is the Butown Theorem. X squared plus y squared equal to z squared. Right. So of course then we take the derivative of everything with respect to t. And that's exactly what we're going to do. So assume everything is a function of t, differentiate that with respect to t. Differentiate that with respect to t. With respect to t. Right. Then we can put the parentheses around the x, the y, and z. So function with respect to t, right? So this is just a chain rule, 2 times that derivative, parentheses square, 2 times parentheses derivative, and then z, same thing. Right, first we have x, then we have y, and then we have z. So we have 2x. X prime is going to be dx over dt. Y dy over dt equal to 2z dz over dt. Because that with respect to t, and this is derivative of x with respect to t, of y with respect to t, of z with respect to t. Right, now the problem is what we are given and what we need to find. Right, so the question asks how fast is the distance between the plane changing. So this is the question. How fast is the distance between the plane changing? Meaning that the distance between the airplane is z. So this is what they ask for, dz over dt. Trying to solve for that. Now, what are the numbers? Right, so let's look at the numbers that we underline. 120 miles per hour, that is due west, and that is mile per hour, so that is the rate. So this should be dx over dt because that's going west. So dx over dt. Right. Now this is where the physics come into play. Remember we did this in section 3.6. This airplane going west, if it is on the right though. So it is on the right, so x is positive, but dx over dt, because the airplane going west, going this way, it is going to be negative. Mile per hour. I mean, there's too many things, so we just try that. So be mile per hour. The negative here because of it going west. So that direction, west. The one that fly north is 150 miles per hour. So this one going up is going to be positive. So we have dy over dt is positive 150 miles per hour. Because if anything that go up or to the right is positive, and left and down is negative. Right, so that is dx over dt, dy over dt, so we know those two, which is good. When the westbound plane is 180 miles from the airport, so x is 180, which is also good, so we know that as well. It is positive because it is on the right. The airport, the northbound plane to the airport, this is 225, but this is at the bottom. I mean, going down at the bottom, be below the origins. So y here is going to be negative 225 miles. Once again, this negative because it is below. So anything that is below, going down on the left or going to the left is negative. Anything that going up, above, on the right or to the right is going to be positive. So that's on the side. So let's put all the numbers we know in, and that's all the numbers we know, right? 2 times x, 180. I'm just going to I'm not going to put the unit here because that look very rounded. we can always determine the unit by the variable at the end. dx over dt, so 2x, dx over dt is negative 120 plus 2y, negative 225, dy over dt 150, and 2z. Too bad we don't know z, because that's all the numbers we have in the problem, right? We need to find dz over dt, so that's okay to leave it there, but we still need to find z first. So scroll down here and then, so what is z? Right, good thing is we have the Butown Theorem. So x squared plus y squared equal to z squared. So if we solve for z, should be plus or minus, but because we're talking about distance here, the z is the distance between them, so z should be positive. So just have the square root of those two, the sum of the square of those two numbers, right? Square root of x 180 plus y, that is negative 225. We don't even need that because the square will turn to positive anyway. So 288 180 square 225 square, and square root of that 288.14, just right, 288, and this will be mile, so we'll substitute in that here, 288.14. dy, dz over dt, we don't know that, but we're just going to leave it, dz over dt. Right, now do all the math on the left hand side. Sorry, my recording program crashed, so I kind of have the cut in the video, but so we have z, put that in here, we're trying to find dz over dt. So everything on the left hand side, if we put in the calculator, 2 times 180 times negative 120 plus 2 times negative 225 times 150. We have that, and divide by 288.14. Actually have that number earlier, so we divide that, and we have negative 384. But we forgot one thing, right? Is there 2 here, which I forgot. So there are 2. So we have this number divided by 2 times that number. Forgot there's a 2. Yeah, there's a 2 here, which I forgot. And so dz over dt. Yeah, so we have that number divided by 2, divided by that, we have negative 192. Yeah, just 192. And the unit of z is mile, the unit of t is hour, so we have mile per hour. So that is the unit, which is good. Now, the negative though, does that make sense? So, the negative, this is the rate being negative, meaning that it's like the slope. If it's negative, it's going down, meaning it is decreasing. So it makes sense because the airplane converts into the airport. So the distance between them will get smaller and smaller. Therefore, the distance between them is decreasing where derivative is negative. So that makes perfect sense here. It's negative, indicates that decreasing in the distance between them. So that's why it makes perfect sense. So that's what we have for that problem. Have another one here. A few more actually. An observer stands 200 meters from the long side of the hot air balloon. The balloon rises vertically at a constant rate of 4 meters per second. How fast is the angle of elevation of the balloon is increasing 30 seconds after it is launched. So a person stands here. Okay. Now we assume the perfect condition that the hot air balloon goes straight up, meaning there's no air, there's no wind whatsoever, so to go vertically up. And also, even though the balloon is going from the ground, but the person do not look from the ground. So assume that the person is not standing like this, more like he lying down and looking up, so the eye level is at the same as the ground. So he just lie with the head on the ground and looking up. So that's what it actually is. So the eye level is here, looking up. Here's the angle theta. Here of course we have the distance, the altitude of the balloon, or y. So we have y here. So here we have y, and then we have look like an angle of elevation, which is theta. Of course, both of them are function of t. Later we'll determine that. Let's underline the important things. So 200 meters will be that distance. It is 200 meters, so we don't need to introduce any variable for it because it's the constant. So 200 meters, that's good. 4 meters per second, that is how fast the hot air balloon going up. And then 30 seconds. The question is, how fast is the angle elevation increasing? So how fast is the angle of elevation increasing? So that is the question. Right, so we have the angle of elevation, hot air balloon going straight up. So is there anything that related all the quantity together in this triangle? Right, so what we see here is we have an angle. Y is the opposite to that angle, right? So this is opposite, and 200 is adjacent to the angle. So what ratio that has opposite and adjacent? So that is tangent, right? So either tangent or cotangent, but we use tangent. So to relate that, we have tangent is equal to opposite over adjacent. In particular, tangent of theta, opposite over adjacent. Simple enough. Now, cross multiply, because just like differentiation, implicit differentiation, simplify the equation if we can, because that makes the derivative a lot easier to do. So cross multiply 200 tangent of theta equal to y. And then so we have the equation that relate everything together. The math differentiate everything with respect to t. We don't even need to know what we have and what we're trying to find, but just differentiate with respect to t once we have the equation. Determine those quantities later. So differentiate. Of course, we assume everything a function of t. I forgot to write that. With respect to t. So assume y, theta and y are function of t. Right. So they are function of t, so I put the parentheses around it so that I know that it's going to be the chain rule. Right. 200, still 200. Derivative of tangent Okay, over there, the derivative of tangent is secant square. So we have secant of something square. And then derivative of that. Doesn't matter what inside the parentheses. And derivative of y, that is just the parentheses prime. Right? Because the derivative of the parentheses itself is just 1. Just like the derivative of x. I mean, that is pretty confusing. Derivative of x is 1. So the derivative of the parentheses, treat that as a variable. Derivative of that is 1. But of course, if this is the function of x, then we have to multiply by the derivative of it. But in this case, derivative of the parentheses, we just put the derivative into it, and that's all we do, right? Or the derivative of the parentheses is 1 if you want to. Right, now theta y. So we have 200 secant square of theta derivative of theta with respect to t. So we will write d theta over dt. And then this is just derivative of y with respect to t. So the right hand side we just have y, take the derivative of that with respect to t. Obviously it's going to be dy over dt. Right, now we'll go back to the problem. What do we know and what we don't know and what we need to find. Right. Assume that it is 30 seconds after launch. So what does that mean? By the way, what is the question? How fast is the angle of elevation of the balloon is increasing? So angle of elevation is theta. So the question asks us for what is d theta over dt. So that is the question. So we're looking for this. Do we know theta? We don't. So how do we find theta? That's what we need to determine first when we substitute in here. By the way, what is 4 meters per second? That is the speed of, or the velocity of the balloon going up, right? So since y is the displacement, so 4 meters per second, so that is dy over dt. This is going to be positive because it's going up. Meter per second. Yeah. So that is dy over dt is 4 meters per second. Now, if it goes 4 meters per second up in the air for 30 seconds, what is that distance? So we said 4 meters per second in 30 seconds. So of course we multiply them, the distance is going to be equal to, multiply them, we have 120 meters. So 4 meters per second going 30 seconds, so the distance y is going to be 120 meters. Right? We still need to go back in here to solve for theta though, because that's what we'll go after. So tangent of theta we don't know. We do know y now is 120 over 200. Of course we take the inverse, we have theta equal to tangent of inverse 120 over 200. Right. So tangent inverse 120 over 200. Is that right? Alright, we'll make sure that this is in radian. So it's good. If it is in degree, this will be 30.9 degrees. But this has to be in radian, right? Because in this calculation. If there's a unit if it is the degree, that will be a lot complicated. So the standard unit for angle is radian, so it's going to be 0.54 or something. 0.54 radian. Right, now we have that. Put it back in here. 200 secant square of, just going to put this in there. 0.54 d theta over dt, we don't need to know, but we're going to find it. dy over dt, dy over dt is the speed of the balloon going up, so that is 4 meters per second. I'm not going to write unit, just leave for there. So we just need to do this. So secant, how do we enter that in the calculator? So secant is 1 over cosine, right? So that's what we have to enter. Secant is 1 over cosine, and this is square. So that's what we have to enter in the calculator. 1 over cosine secant, and then the square. Over 4 equal to 4. Right. Now just do in the parentheses 1 divided by cosine of 0.54. Actually, don't. It's better just say cosine of, copy and paste, that better. And then we do the cosine ready, reciprocal, and then we square it. So all of that is about 1 multiplied by 200. So the left hand side we have about 200.02 d theta over dt equal to 4. And so for d theta over dt, we have d theta over dt equal to that divided by, 4 divided by that. We have about 0.019, so about 0.02. And the unit will be radian per second. Right, so that's all we have. Right, next. A jet ascends at an angle of 10 degrees angle from the horizontal line with an airspeed of 550 miles per hour. We need to change that in the note. How fast is the altitude of the jet is increasing? So in this case we don't have the picture, but we have to draw horizontal. The jet going at 10 degrees. This is constant. And then the question we have, how fast is the altitude of the jet increasing? So this is the question. We do have the 10 degrees, which is that. The airspeed, so the airspeed, because the speed of the jet going 550 miles per hour. So we have that. Right. So how do we relate everything together? So let's say this is y, this is x, and this is z, like we normally do. In this case, we not worry about x because that's not mentioned in the problem. It only mentioned that 50 miles per hour. So that is the speed of the jet that going straight going up in that direction. And then we need to know y, so we don't really have x in here. So how do we relate all the quantity together? So in this case, like I said, only y is relevant. That is the altitude, and then z is relevant because that is the jet, and it's going straight up. So what we have here is the relation of an angle, which is having the opposite and hypotenuse. So we have sine is equal to opposite over hypotenuse. So in this particular, we have sine of 10 degrees equal to opposite, which is y over z. Once again, cross multiply to simplify the equation. So z sine 10 degrees equal to y. Now, of course, we assume everything a function of t and take derivative with respect to t, right? So differentiate that equation. Sine of 10 degrees is a constant. Make sure it is in degree mode if we need to. So that is in degree. Oh. We have to do this one again because that is in radian. Okay. Sorry, go back to the last problem. Make sure in radian mode. Okay. Do this again because when we enter it, it is equal to in degree. 200 times 1 divided by cosine of, we still have that number. Oh, I delete that number. I just say 0.54 then. Square. Right. So that. And then, so that is not 200, that's 271. Yeah. So if this is in gradient, this should be 271.86. And we take 4 divided by that. It's 0.457, so a little off here. Yeah, so it's very important that we have to enter the correct unit. Sorry. Yeah. When I go back and check, this actually is, yeah. So when since we calculate based on using radian, in calculation we put it back as in radian. Yeah. Alright, sorry about that. Let's go back and check it. Yeah, it's just the calculator. Right, now sine of 10 degrees, if we want to make sure it is in degree, sine of 10 degrees is about that. That's not very important. Equal to y. So we differentiate this with respect to t. Of course, we assume that both of them are function of t. Y, z are function of t. Right. So we just do that. And so to test the constant, so we put the function of t, right? Derivative of that times the constant, derivative of that to test. Sine of 10 degrees. Y is here, z is here. Right. These z prime to the derivative of z with respect to t, so that is dz over dt. Sine of 10 degrees. Y, derivative of y with respect to t, dy over dt. Right. Now what do we have? How fast is the altitude of the jet increasing? So definitely they're asking for dy over dt, right? Because the airplane going at that angle, the distance of course is also increasing. And then dz over dt, we know the speed of the jet. So this is dz over dt, 550 miles per hour. So we have everything. We don't need to, so that 550 into here and sine 10 degrees. So dy over dt that 550 times sine of 10 degrees. So that times 550 is 95.5. The unit for y, that is mile, and t time is hour, so the unit is mile per hour. It is positive, which is good because that is increasing. So that's what we have. Right. Once again, go back and change that. This should be in radian. Okay. Next we have another problem. An invert conical cone of water tank with the height of 12 feet, the radius 6 feet, is ran through the hole in the vertex at the rate 2 cubic feet per second. What is the rate, the change of water depth when the water depth is at 3 feet? So try to draw a cone. Right, let's draw a cone. And this is the invert conical water tank, so this is a cone. Right, the water will pass and out from the vertex. The water tank though, the height is 12 feet. So the height of the tank is 12 feet. The radius 6 feet. So that is the radius, which is 6 feet. And the water coming out from the bottom here. Right. And what is the rate of change of the water level or the depth of the water when the water is at 3 feet. So when it is 3 feet, which is about half of this, so it's about this much. So when the water is at 3 feet, what is the rate of change of the depth? Right. So we have the height, the radius, and the volume. So that's more like the volume of a cone. With radius R and height H is V equal to 1/3 pi R squared times H. So in general, the volume of the cone is 1/3 base area times the height. The base area, this is a circle, so just pi R squared times H. So that's what we have. Furthermore, if we want to simplify things, because here we have both R and H, because this is a cone, the relation of them is fixed. So let's just cut this in half. I'll explain why we have the fix. So I have a cone like this. Originally this is 6 and this is 12. So when the water level is at any time for H and R, we have to have a similar triangle, right? So a similar triangle gives us 12, the whole thing divided by H is the same thing as 6 divided by R. So ratio and proportional. In this case, similar triangle. Cross multiply 6H is equal to 12R. Right. Now, this is where we go back to the question and say, do we need the height or do we need the radius? So let's look at the problem. The height is 12 feet, 6 feet. We used that already, so that's not going to help us. The rate is very important. So this is 2 cubic feet per second. So cubic feet, that has to be the unit of volume over second. So this definitely is dV over dt. But to be precise, dV over dt has to be -2 cubic feet per second. And you may ask, why is that negative? Right, so the problem, the water level coming down, the volume gets smaller, 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 right? The volume of the water coming out will be equal to whatever left, whatever the water on the cone, on the tank, will be less with. So rate of change is 2 cubic feet per second. It has to be negative because the volume inside the cone is going to be decreasing as the water coming out at the hole at the vertex. So this is negative because it is decreasing. Right, so we have that. And at what rate the water depth? So we worry about the depth, meaning that we're going to ask to find dH over dt. Right, and so of course, what is the R over dt? Of course, then I guess we can just continue like we usually do. We can just work from here. Right, so notice that we have this equation as well. Now, of course, from here we can just substitute back in here and solve for R, or solve for H if we want to. In that case, it's V and H and R, but we don't need to do that. Remember, assume everything a function of t and take derivative. Assume H, R, and V are function of t. And then we differentiate. Once again, this will be much better if I multiply everything by 3. If multiply 3 on both sides, I don't need the 3 at the bottom. I have 3v equal to pi r squared h. So I will differentiate that. With respect to t. Right, so all of them are variables of t. The pi is a constant though. So 3v on the left is easy. Derivative on the left hand side is going to be 3 times derivative. That's easy. On the right hand side here, notice we have the function of t times another function of t, so that is a product rule. So u is pi r squared, v is h. This is little v. U prime is going to be 2 pi put the parentheses around that, give us 2 pi. Oh. Let's slow down a little. It's going to be pi and something square, so it's going to be 2 times that. And then r inside. So that gives us 2 pi r, and then r prime will be dr over dt. V is that, so v prime is just dh over dt. We just want to do that. Perfectly fine. dh over dt. So of course we substitute that into this equation. There's a lot of space, so let's just write from here. 3 times equal to u prime will be that. U prime times v plus u v prime. Now let's put all the numbers we know here. By the way, v prime is dv over dt. Equal to 2 pi r h dr over dt. Plus pi r squared dh over dt. So yeah, so that is the derivative. Right, so what do we have? dv over dt, that we know for sure. We know the depth at the water at that moment is going to be 3. So h is equal to 3. If h is 3, we can solve for that easily. 6h, 6 times 3 equal to 12r. So r is equal to 18 divided by 12, so 1.5. So r is equal to 1.5, which is always, the radius is half the height in this case. So the radius is going to be 1.5 is 3. Furthermore, we have 2 rads here, that kind of a problem, right? Furthermore, from here, of course, we can divide by 6 on both sides, h equal to 2r. Now, since both of them are function of t, if we differentiate this with respect to t, so just to check the derivative with respect to t, give us h so that gives us dh over dt equal to 2 times dr over dt. Or in this case, what do we ask to find? What is the rate of change of the water depth? So that we ask for to find dh over dt. So dh over dt is 2 times that. So we have to solve for dr over dt. It's going to be 1/2 dh over dt. Now with that, we substitute everything we have in this problem. The volume though is -2. 2 pi r at that moment, r is 1.5. H at that moment is 3. H dr over dt at that at any moment, it's going to be that 1/2. So we substitute this into dr over dt, so that's will be 1/2. Just want to stand out here. One-half dh over dt plus pi r is 1.5 square dh over dt. Right, give us -6 equal to, right, multiply straight across, 2 and 2 cancel out, right? 3 times 1.5, that's 4.5 pi. Pi dh over dt plus 1.5 square is 2.25. 2.25 pi times dh over dt. Right, combine like terms, 4.5 plus 2.25. 6.75 pi times dh dt equal to -6. So the h dt is equal to -6 divided by that. And we have dh over dt is -0.283. The unit for height will be feet. The unit for time is second, so feet per second. meaning that the distance will reduce by negative 0.2833 feet per second. At that moment, it's not constant. The height is not the thing that constant here is the volume, and just the volume decrease as a constant rate. Of course, at that moment when it is 3 feet, that the speed or the rate of change of the height is given by that. So that's what we have. So the bottom line is, in this section, relative rate. So we come up with the equation. When we have the equation, assume everything a function of t. Take derivative with respect to t, and then put in the information that we are given, and then look for the information that we're asked to find. So in this case, we ask for the change of the water depth, which is dH over dt. Right, so that's all we have. So that's the end of chapter 3. As always, thank you for watching, and see you in another video in Calculus 1.